Okay, video number 2. It's 1 o'clock and I'm ready to go to bed. So I put this question on here for the exercise before we actually launch into the notes from page 7 through 9 on the LHopitals Rule. The reason I put this in the notes is because you guys did really great on this question, at least my students did, and many of my students did not do well on this one. I did look at Schwartz's to see what her answers were on this one. The reason most people got this one wrong is because many of you correctly identified the numerator, negative 2x must be equal to 0, to get a horizontal slope. Many of you also thought, oh, just divide the negative 2 over, so x equals 0. And you guys went with these two options. And I should put these in red because they were wrong. So I'm going to show you how to do it right now. If you want a horizontal slope, that means you want dy to be x equals 0. So we're going to set 0 equal to negative 2x over y plus 1. And now let's see what happens. I'm just going to add the switch over here. Not really switch, I'm just going to move that over, sorry. And what I'm going to get is 2x over y equals 1. And then multiplying by y, I get 2x is equal to y. Oh, look at that. There's our answer. And that's how you need to do the problem. Again, most people missed it. That's why I put this problem up here. A little bit tricky, but if you use the information they gave you, particularly that horizontal slope part, that's the key to solve the problem. Let's go on to the problems that we have for today. So this is LHopitals Rule Day 2. We are on page 7, and I have not met a student who did not like LHopitals Rule. LHopitals Rule, again, was that idea that Ms. Schwartz was saying, is that if you have an indeterminate form for LHopitals Rule, for our case, it will strictly only be 0 over 0 or infinity over infinity. Then, your original limit is equal to the limit of their derivatives. Now, Ms. Schwartz did not tell you a very important fact, which is also true. If, let's say, you get 0 over 0 or infinity over infinity here, and let's say you also got 0 over 0 again, or infinity over infinity here, what you can do is actually take successive derivatives each time. And until you actually get something that you want, you can go as far as you want with these derivatives here. I'll show you an example of that on the following examples. So again, we're only going to deal with 0 over 0 or infinity over infinity. We will not do the other ones, and I think Ms. Schwartz might have alluded to this, but honestly, I didn't watch the video. We have 0 to the 0 power, we don't do. We have infinity to an infinity power, we don't do. We have 1 to an infinity, don't do. We have 1 to the 0, that's 1 to the 0 is just 1. Let's see, there's another one. Infinity, 0, 0, 1 to infinity. Oh gosh, I'm forgetting one of them. But anyway, these types are for BC. We strictly, in this class, will only do, you will only see problems that will have a potential of getting 0 over 0 or infinity over infinity. Okay, so now, let's go to the meat of this here. So what is the limit as x approaches 0? E to the x minus 1 divided by tangent x. Well, first thing, let's evaluate, man. Let's see what we get. If we plug in 0, I'm going to e to the 0, which is 1. 1 minus 1, which is 0. So I get 0 over tangent of 0, tangent of 0. Tangent of 0 is going to be this point. That's 0. Okay, so 0 over 0. Okay, so I need LHopitals Rule. So LHopitals Rule here is going to be equal to the limit as x approaches 0 of the derivative e to the x over tangent, derivative tangent is secant squared x. Many students have the misconception initially of doing a quotient rule here, but I want to remind you that when you do LHopitals Rule, you're doing strictly the derivative at the top, strictly the derivative at the bottom individually. You're not doing a quotient rule here for 12. Yeah. Oh, man. Let's go and evaluate. Plugging in 0 again, we get e to the 0, which is 1 over secant of 0 squared. Secant of 0 squared. Well, let's just do some side work here. Secant of 0 is the same thing as 1 over cosine of 0. Cosine of 0 is right here. That's going to be 1. So this is 1 over 1. So when you square 1, you get 1. All together, you get 1. See? Let's go to this one. Okay. Well, when x approaches 1 from the right, the plus sign means from the right of x over ln x. A little bit of a doozy because of the plus. My thing, ignore the plus. It just means that on your graph, wherever x equals 1 is, you are just looking on this side. That's what that plus means. It's totally irrelevant though, because when you plug in 1, something magical happens. What happens, Mr. Lincoln? Well, if you wait just a second and let me write down, I'll tell you. So if we get 1 in the top, we get natural log of 1 at the bottom. Natural log of 1 is 0. Undefined. Can't do LHopitals Rule. That brings me to a note that I want to make here. So LHopitals Rule works when you get 0 over 0 or infinity, but if you ever get some number not 0 over 0, that is equal to infinity, man. Either plus or minus infinity, you have to judge it based on the top number. But if you get some number that's not 0 over 0, that answer for the limit is going to be plus or minus infinity. And I have terrible notation here. So I just want you to be aware that this is only with limits. You get a plus or minus infinity. Okay. Let's go into this problem. So 1 over 0 is undefined. I don't see an undefined option here. So if I did 1 divided by a really small number like 0, I'm going to get a really big number that's positive. E is the answer. But not this E. It's not that E. It's the letter E. Oh, scary. Okay. Find all values k. Now, I actually didn't show you an example where you would use the second derivative one. You do that. Okay, I'll do that. I'll do it. I will do it. Okay. Let's go ahead and go to, let's see here. Okay. Let's go ahead and do when this x approaches 1 of k. Okay, so let's evaluate here. I'm not going to multiply anything by x minus 1 here because I don't want to keep this as an identity here. I'm not going to touch that 5 yet. When I plug in 1, I get k plus m times the natural log of 1 over 0. There's a limit here. And I get natural log of 1 is 0. 1 is going to be k plus 0 over 0. Okay, now that's weird because now I get k over 0. I can't have k over 0 though, because if k is a number, any particular number other than 0, so let me write this out because that's kind of important. If k is any number other than 0, you would get an undefined value for the limit. Value for the limit. But the limit is 5. That means that k must be 0. Okay, so k is 0. The reason I know that k has to be 0 is because they want me to do a LHopitals rule, which means that I want this value to be 0. Circle around looks like a 0. That's funny. So let k equal 0. 0, and then that sets up a LHopitals rule. So now let's do a derivative. The limit as x approaches 1 of the top's derivative is going to be derivative k is 0, so 0 plus the derivative ln of x is going to be 1 over x with an m on top, divided by the derivative of x minus 1 is just 1. No, let's clean this up here. So now this is going to be equal to the limit as x approaches 1 of m over x. Okay, now we want this limit to be equal to 5. And when I plug 1 in, I get m equals 5. When x equals 1, m equals 5. Okay, well, there I go. So my two answers, k equals 0. If k equals 0 and m equals 5, that limit will equal 5, which is what I want. And I just want to, again, remind you that this was a tricky problem. It kind of relates to the other part that we did in the opener. Be careful with this ideal. Super scary. Okay. I'm going to go ahead and just show you one example that's not on your package, so you feel free to write this anywhere, where you could use the LHopitals rule a little bit more often than just this first derivative. Let's do the limit as x approaches 1 of, let's do x minus 1 squared over, let's do, let me make sure this works, x cubed minus 1. Let's do squared. I think this will work. Let me pause and double check. Okay, 45 minutes later, it works. Just kidding. It's only like 30 seconds later. Alright, so if I plug in 1 over 1 into both of these, I get 0 over 0. So that's great. That means I can use the LHopitals rule. Hooray! So let's go and take the derivative here. I get the limit as x approaches 1 of 2, so taking derivative of the top is 2x minus 1. I'm going to put it times 1 because that's a chain rule. And then on the bottom, I'm going to get that 2 comes down in front, so I'm going to get 2x cubed minus 1. And then I need a chain rule here times the derivative of x cubed minus 1, which is 3x squared. Okay, let's go and cancel those out. And if I just rewrite this, no need to really rewrite it, but I'm going to just rewrite it just to be clean here. We get x minus 1, 3x squared times x cubed minus 1. Okay, let's see what the damage is. If I plug in 1 again, so 1 minus 1, I get 0 on top. 1 cubed minus 1 is 0. Doesn't matter what this is because it's on the bottom. So I need LHopitals rule again. Okay, and this is an example where I can use LHopitals rule consistently until I get some number that's some value that's a number, or something like 0, a number that's not 0 over 0 that will give us an undefined value. Okay, so let's do another derivative here of top. So I get the limit as x approaches 1 of the derivative of the top part is just going to be 1. The derivative of the bottom is going to be a product rule. So we'll do 3x squared, the first, times the derivative of the second, which is just 3x squared, plus the second, times the derivative of the first, which is 6x. Okay, now let's evaluate our limit and see if we got lucky here. So if we plug in 1, we get 3 times 1, which is 3 times 3, plus 1 minus 1 is 0, so plus 0, it's over 1. It's under 1 rather, which is 1 over 9. So this limit is 1 over 9. And this would be an example of where you could use LHopitals rule multiple times until you actually get a value that you may have been expecting. I do want to also point out, though, that sometimes if you're a little bit more savvy with your algebra, you could kind of avoid a lot of work there because doing that product rule is kind of not exactly fun, for me at least. So I'm just going to show you how you could have done this problem without necessarily doing all that work. If you do the limit as x approaches 1 and avoid LHopitals rule, well, you get x minus 1 squared here, but factoring x cubed minus 1 with SOAP gets you x minus 1 times x squared plus x plus 1. But because since the original quantity is squared, both of these values are squared. And when you plug in 1 now, because x minus 1 and x minus 1 squared is cancel, You get 1 plus 1 plus 1, which is 3. 3 squared is 9, which is the answer that we had before. Again, how much do I expect you guys to actually recognize that? You should be able to solve this limit, though. Either way, either using some algebraic method, or LHopitals Rule, or a calculator, if it was allowed, things of that nature. Let's go on to the last problems. I think this is just, 2 more problems. I'll go faster. Okay, the limit as x approaches infinity is both infinity for f and g, sorry. Oh, that's embarrassing if you heard that. Okay. So, they're telling me that the limit as x goes to infinity is infinity on the top, so I get infinity on the top. For g, it's infinity as well, so infinity on the bottom, which means I can use LHopitals Rule. So now, this limit is going to become equal to the limit as x approaches infinity of f prime of x over g prime of x. Again, infinity over infinity was one of the indeterminate forms that we could use LHopitals Rule. And the limit as x approaches infinity is going to be 1. So it looks like it's just going to be 1 for all values. So we have 1 over e to the x. So let's go and rewrite that. Limit as x approaches infinity of 1 over e to the x. Well, now let's see what happens. I'm going to have 1 divided by a large number. 1 divided by a really big number is equal to a very small number, like 0. B. And for the final one, find the value of the constant k, which makes f of x equal to that. Alright, well, let's see here. If I plug in pi over 2, let's see here. So, just to remind you, continuity is that the limit as x approaches pi over 2 of f of x needs to be equal to f of pi over 2. Okay, so that's a little review of continuity, which means we need a limit as x approaches pi over 2. Well, if we do the limit as x approaches pi over 2 of sine of x minus 1 over x minus pi over 2, I'm going to bet we're going to get an indeterminate form here. Sine of pi over 2 is 1 minus 1, that's a 0, over 0, the LHopitals Rule. Okay, so now let's go and do the LHopitals Rule here. Keep the limit, but take the derivative. Derivative of sine of x is going to be cosine of x. Derivative of x minus pi over 2 is going to be 1. Now let's try that value again. The limit as x approaches pi over 2. Cosine of pi over 2 is 0. So I get 0. So if this limit is supposed to be equal to 0, well, that means f of pi over 2 is also equal to 0. K is 0. Thanks for watching, guys. Oh, make sure you read that bottom part. It's funny. We do really wait till the end to teach you LHopitals Rule, but it's kind of a gift. Have a good one.